Hi, in this video I wanted to discuss how we can use GeoGebra to help us understand what the integral of a piecewise defined function should look like. Okay, so let's go over to the document camera and look at some examples here. Okay. Now typically when a student thinks about evaluating an integral, let's say, okay, integral 0 to 5 of I don't know, t squared dt, they say, okay, well, we can do that. That's pretty easy. This is a power function, so we increase the exponent by 1. We get t cubed. We divide by the new exponent, so we get t cubed over 3. We evaluate that at 0 and 5. So we get 125 over 3. All right. And of course, this is using the fundamental theorem of calculus. Okay, and that says if there exists f of x with f prime of x equal to little f of x, then the integral from a to b of little f of x dx is equal to f of b minus f of a. All right, so in other words, these definite integrals can be computed using antiderivatives if they exist, but that's not what a definite integral really is. A definite integral is really a limit. It's the limit as n goes to infinity of this sum, I equals 1 to n, f of xi delta x. Okay, typically called a Riemann sum. Okay, so you don't need to be able to find an antiderivative to talk about an integral. All right, so here we are looking at GeoGebra, and let me go ahead and input a piecewise defined function here. So we'll do f of x equals, and of course we know that the if command will let us put in a piecewise defined function. So let's do if x is less than 2, then I'm going to hit the right arrow key, and if x is less than 2, then this is going to be, let's make it x minus 1, and if x is greater than or equal to 2, okay, let's see, what should we make it? Let's do 4 minus 1/2 x. Okay. So that is our piecewise defined function in GeoGebra. It's got a break right there. Okay, so let's imagine I wanted to talk about the integral of this function. Okay, so I'm going to do some stuff here. Firstly, I'm going to get a little point that slides along the graph of this piecewise defined function. So let me go to my Tools menu and select a point. And I'm going to click directly on the graph of the piecewise function. And I can go ahead and go back to the calculator. That's all I needed from that menu was the point tool. And I want you to notice here that no matter how hard I try to pull that point off the graph, it won't come off the graph. I can slide it left to right. It'll even go from piece to piece. Okay, but I can't pull it off the graph, so it's kind of stuck on there. And that's what I want. That's good. Okay. Now, I'm going to make GeoGebra give me a number. I'm going to say let little a be 1 comma 0 times that point capital A that we just talked about. All right. Now, I want you to notice something here. The value of little a, look at the relationship between the x-coordinate of the point capital A and the value of little a. Okay, so notice all I've done there is I have created a number that gives me the x-coordinate of the point on that graph. And here's what we're going to do. We're going to do integral. Okay, now notice we get a lot of options here. I want this one. I want a definite integral. Okay, the definite integral of the function f. The start value is going to be 0, and the end value is going to be a. Right, so it's integral from 0 to a. And notice what we can see in the picture here, right? We can change the position, and it'll integrate from 0 up to that point. Notice we're using the interpretation here of integral as area under the curve. It's a definite integral from 0 to the x-coordinate of our point. All right, so we got that there. Okay, and now I'm going to define another point, capital B. The x-coordinate is going to be little a, and the y-coordinate is going to be b. Okay, notice right there. Okay, so as I move a around, b will also move. Okay, and here's a neat little feature that you can use on GeoGebra. I'm going to right-click on the point B and say Show Trace. So the way I think of this is, imagine we took that point B and we soaked it in ink. And wherever point B is on the graph, it leaves the ink. Okay, so little b, that number right there, is the area under the graph from 0 to a. Okay, so it's like the integral. Okay, so the graph that we're tracing out right here is the integral of my piecewise defined function. Okay, so here's what I want to do. I want to say, what's the formula for that graph? What's the curve? Okay, what's the equation of the curve? Well, we can see right here, I would suspect there's a change in the formula. You see that right there? And it's not a coincidence that's the same place that our original function changes its formula. Okay, so I'm just going to take a shot in the dark right here. I'm going to define a function h, and it'll be a piecewise function, so we're going to do if, and then if x is less than 2, here's what I'm going to do. I'm going to do this. I'm going to do 1/2 x squared minus x. And now what am I going to do otherwise? Okay, I'm going to do 4x minus 1/4 x squared. Okay, so that's going to be my function. All right. Now, let me see here. Okay. Let me zoom out a little bit here. Now you can see that's the function h of x I just defined. So it is agreeing with the trace over here, but it's not quite good enough, right? Because over here we see that it is missing where the trace is. Okay, so let me switch to the document camera and show you what my thinking is. Okay, so we had defined our piecewise function f of x to be, it was x minus 1 if x is less than 2, and it was 4 minus 1/2 x if x is greater than or equal to 2. Okay, so I was trying to come up with this function here, 0 to x f of t dt. And this was my guess. Okay, my guess was 1/2 x squared minus x if x is less than 2, and 4x minus 1/4 x squared if x is greater than or equal to 2. Okay, so hopefully you notice a connection here, right? To get this, I just integrated. I took the antiderivative of this first line. and then I took the antiderivative of that second line. Now let me switch back. Let's go back to the view of GeoGebra over here, and we can see, you notice it's just like this part is just too high. It's up there when it should be down here, okay? The value being traced out by the point B, that's actually the one that we want. So simply finding the antiderivative of each curve individually, let me switch back here, simply finding the antiderivative of each curve individually doesn't quite work. And you probably, I bet you can understand why. Okay, this is an antiderivative. Okay, it's not the antiderivative. Okay, so if I were to do this, 4 minus 1/2 x dx, 4x, yes, I integrate this, I get 4x. I integrate this, I get 1/4 x squared plus c. Okay? So here's what I need to do. The question is, what value should c take? And I want to choose a value of c over here that makes this part of the curve match this part of the curve right here. In other words, I want to lower it down a little bit. So let me show you how we can figure out what value c should take on. Okay, so I'm looking right here, and I'm seeing that when x equals 2, this first line, okay, that becomes, okay, and let's see, what does it become when x equals 2? And when I say that first line, I mean this one right here. It becomes 1/2 2 squared minus 2. Okay, so 1/2 2 squared minus 2, so this looks like, oh, this looks like I'm getting 0. Okay. Now, we want to choose c so that when x equals 2, the second line also gives me 0. So in other words, I want this expression to be 0 when x equals 2. Now, the good news is this is an equation in one variable. I can solve it. Okay, so 4 times 2, that's 8, minus 1. So this looks like it's 7 plus c equals 0. So I should use c equals minus 7. So let me switch back to GeoGebra here. Okay, so I bet if I change this last part over here, make that a minus 7. Okay, and now let's look at what's happening here. Notice it agrees with that point that we're tracing out here. Okay, so it's this function right here that is the true integral of our piecewise defined function. All right. So the theme here is, okay, you want to integrate a piecewise defined function? Great, you can do that. You integrate each line individually. But what you need to do is when you switch rules, you have to make sure you choose the c appropriately. Okay, now there's a reason here that we're concerned about what is happening when x equals 2. And that's because that's when we switch rules. We have to look there to make sure the two graphs line up.